Bismillahirrahmanirrahim. Good afternoon, everyone. Today we will talking about the most important information about the diode, the Schottky diode, and why this kind of diode is very important to us. Why it has different shape. For example, here has three legs, is different from the other. Like we know that all the ordinary diodes has two terminals, anode and cathode. Here was the story behind these three legs and why this kind of diode is expensive than the other. Now let's go to the deep information related with this topic, Schottky diode. Now let's talk about who invited this diode. This guy, he was German physicist. He was Walter Schottky. This field was depend or belonged to semiconductor technology. Has many names like power diode or temperature carrier diode. The first use to this kind of diode was as a power element in rectifier circuit. Like we know, like we're seeing here, this diode has two different shapes. The first one was like any ordinary diode, has just two terminals, anode and cathode. But here the second shape is very different from all the ordinary diodes, because here this kind has three legs. And like we know, any diode has two terminals, anode and cathode. What the story behind the third legs? We will know what that means, the third leg and this diode, and what the main difference make this diode is different from the other. And because that we can say this one feature from his many features make it important and expensive from the other. Now, like we know, this Schottky diode has two different shapes, two terminals, and the other one has three legs, or we can say three terminals. Actually, no three terminals, two terminals, but the leg at mid at both of them. It's something like a Schottky barrier, and we will talk by using deep information about that at the next slides. Now let's do a simple comparison between Schottky and ordinary diode. From the shape, we can say it's different. The second figure was different from ordinary diode, and like we're saying, has three legs and different shape. And at the same time, it's expensive from the other ordinary diode. And the important point is the voltage filling on the diode varies between 0.6 volt until 1.7 volt. Actually, these two numbers, it's not small yet, not small. And if we do simple comparison with Schottky diode, we will see here start from 0.15 volts to 45 volts. That means at the maximum point, at the maximum number here, they didn't reach 1 volt. Here, this the one of the important advantage, make the Schottky diode be featured from the other, and we will explain why at the next slides. And at the ordinary silicon diode, the power losses are bigger than the Schottky diode. Current values are bigger than the current values at the Schottky diode. Ordinary diode is slower than Schottky, not Schottky has different situation from the other ordinary diode because it's faster than, and we will take the information about, explain why at the next slides. Now, like we see here, Schottky diode has three legs, and here some figure like two diodes at reverse each other. Here, let's talk about the structure of this diode. Like I said before, has three legs. The first one is the metal part. It shows like the anode and will be instead of the P side. Is made from usually gold, silver, or platinum, or we can use another materials, but all of them were expensive than silicon, because that this kind of diode, Schottky diode, is expensive than the silicon or ordinary diode, and this one feature make this diode expensive than the other. And the other one is because this kind of diode has many features than the ordinary diode. But like we know, gold, silver, platinum, it's not cheap at all. The second leg at the Schottky barrier will be at the mid between these, between these two legs. It's the junction between the metal and semiconductors. The last one is the silicon part, is the cathode, has the negatively charged. Here, the Schottky diode is known for, actually, Schottky diode has many advantages, but the most of them is, and the most famous of them is the low forward voltage and fast switching ability. This makes them an ideal choices for radio frequency application and at any device with low voltage requirements. The uses for the Schottky diode, because his advantage, we use it in many applications in our life, in power rectification, multiple power supplies, and in solar cell, and something like that. Let's start from power rectification. Schottky diode can be used in high power application. These diode will waste less power. Like I said before, when do comparison between ordinary diode and Schottky diode, use less voltage than the ordinary, use less current from the ordinary. That's mean power equal IV, because the Schottky diode use less power, less voltage and current. That's mean it use actually less power than the ordinary diode, ordinary diodes. Yes, may it reduce the size of heatsink. Heatsink, something like this is still here, something like means work to make the temperature decrease at this kind of diode. Multiple power supplies, it can also help to keep power separated in a dual power supply setup, like with what? Like a main supply or battery. Here, let's talk about the solar cell, why this diode is very important in solar cell system. Schottky diode can help to maximize the efficiency at the solar cell with their low forward voltage bias. Like I say, we just until now we're talking about forward voltage drop. I didn't say any information about reverse bias or reverse voltage drop, because like anything in our world, in our life, like has advantage, has disadvantage. The most important disadvantage to this kind of diode, has a high voltage, a high reverse voltage, because that we dealing with this diode like just by using the forward bias, the forward technique, sorry. Also help to protect our system, like or protect the cell from reverse charge. we know at solar cell, we facing something like leaking charge. When we use the Schottky diode, sorry, we will protect our system from this leaking. This diode will be something like wall, will prevent this leaking charge. Clamping, the last uses to this Schottky diode is clamping. Schottky diode can also be used as a clamp, but within what? Within a transistor circuit. The advantage for using a Schottky diode, low forward voltage drop, like I said, 0.3 until 0.4 voltage is very small amount. This allows a Schottky diode to consume voltage smaller than standard diode. And we will take example by use to image at the next slide. That and the ordinary diode, like we know, consume 0.6 volts, start from 0.6 volts. That's clear. 0.3, 0.4 is smaller than 0.6. That means we can prevent 0.2 volts. The difference between them will be 0.2 volts. Here, this diagram illustrate to us the relation between the forward current and the voltage. The Schottky diode will start before 0.4 volt. Like we said, we can say will start from 0.3 volt, and after that will start to increasing exponentially like that until 500 milliampere at near from 1 volt. This exponentially relation, exponentially increasing, suddenly increasing. But the ordinary diode starts from 0.6. Here, this clearer example here, the Schottky diode, the conventional silicon diode, consume 0.7, 0.6, here consume 0.3. The difference between them is 0.4 volts. When we dealing by using these two different diodes with the same power voltage independent voltage source. Let's take 2 volt. When I will consume 0.7 volt, that's mean here I just can prevent 0.3 volts to my device. But here the situation is different. Here I can prevent 1. I can save. I can take pure voltage to can give it to our device, to my device. Here I can save just 1.7 volts. 1.7 volts at Schottky diode, it's bigger than 1.3 here, because the Schottky diode just consume 0.3 volts at this situation. The ordinary diode consumes, like I said at the last slide, consumes 0.7, leaving only 0.3 to power the load. The Schottky diode consumes only 0.3 volt, leaving 1.7. That's mean leaving bigger amount voltage to power the load. If our load required 1.5, what the appropriate, what the better select to us, what the better situation to us? We dealing with ordinary diode or Schottky diode? Sure, we must use Schottky diode if we have, because at small amount of voltage source, we can save 1.2 pure voltage amount will be 1.2 when we're dealing with Schottky diode, but when we're dealing with ordinary diode, we will save just less than 1 voltage. faster. These are another advantage. Faster recovery time. Let's say why this Schottky diode has this feature. The small amount of charge stored within a Schottky diode makes it ideal for high-speed switching application. That's mean why? Because it has a small amount of charge stored within a Schottky diode. Less noise and better performance. The Schottky diode will consume less power, like I said before, and can easily meet low voltage application requirements. Now, like I said before, the main important disadvantage, it's more reverse current than normal diode. Because that we dealing here at our lecture just with forward bias. How a Schottky diode works. Typical diode combines, like any diode, has two terminals, cathode and anode, p-type and n-type. The p-type will show the metal side, and n-type semiconductor will be the silicon doped with phosphorus, belong to group 5. To form a p-n junction in a Schottky diode, metal replace the p-type semiconductor. This metal can range from a platinum, tungsten, molybdenum, and gold, because that, like I said before, it's expensive than the ordinary diode. When metal is combined with an n-type semiconductor and material silicon junction is formed, this junction is referred to as a Schottky barrier. Here in the next slide, the behavior of the Schottky barrier will differ depending on whether the diode is in n-biased, forward biased, or reverse biased state, like the ordinary diodes. But here we will facing some difference. Like, let me use this diagram. Here the normal diode, p-type, n-type. What does mean? That's mean the both of them terminals are made from silicon, but here silicon doped with boron, for example, belong to group 3, and here doped with phosphorus belong to group 5. But here the situation is different. We're dealing with two different material, n-type doped with phosphor, and here doped with metal. And the same situation here, we will facing depletion region and voltage barrier. Let me explain that at next slide by use the appropriate diagram. Here, the metal n-type doped with group 5 with phosphorus. Here, the majority are electrons, minority are holes. But here, we have depletion region like ordinary diode, but here the negative ions space is smaller than positive ions space. When we put all of them together, when we made this diode, the electrons at the metal will start to try to cross the depletion region to going to n-type. Let me use the details. Unbiased state, free electron will move from the n-type semiconductor to, maybe I have wrong here. The free electron will move from n-type semiconductor to material. It's wrong. How I can, yes. The electron at the n-type will start to cross the depletion region to go to the material side. The material, in order to establish balance, that means the depletion region started to to create it. This flow of electron created the Schottky barrier, where negatively and positively ions meet where? In the pleasure region, and here positive ion space smaller than negative ion space. Free electron will need a greater supplied energy than their built-in voltage to overcome the barrier. Let me repeat that. Free electron will need a greater supplied energy. This free electron will need more energy to support it than their built-in voltage. To why? To overcome the barrier. That's mean the electrons need energy to support the electron to can overcome the barrier. Here forward bias states, that means here we will using power supply. Forward bias, that means metal will show the p-type. The positively side will connected with positive side of the power supply and negatively with n-type. Connecting the positively terminal of a battery to the metal and negatively terminal to the n-type semiconductor will create a forward bias state. In this state, electron can cross the junction from n-type to metal if the applied voltage is greater than 0.2 volt. That's mean here something will be like condition. We must have voltage applied amount more than 0.2 volt, and here this is wrong because the electrons will start to move from n-type going to metal side. I'm sorry about this mistake. And this results in a flow of current that's typical for most diodes. Now the last state is reversed bias. That's mean here, let me use this diagram, this image, sorry. Reverse bias, that's mean positively with n-type, negatively with metal. Here we will see the pleasure region. The pleasure region after connected with power supply will create it, but here the positively ions will be bigger than negatively ions. Here, without any carrier charge, the carrier charge just will be here and here. Here the majority is electrons and minority is holes. Connecting, like I say, the state expands the Schottky barrier. The Schottky barrier, that's mean the pleasure region. That's mean here that the pleasure region will be bigger than forward bias. And it prevents the flow of electron current. That's mean here the bigger the pleasure region, that's mean something like wall will try to prevent the electric current, prevent the electrons to move, to cross to another side, because that will prevent the electric current. If the reverse bias voltage continues to increase, what will happen? This can eventually break down the barrier. And I will use diagram to explain these few words. So will allow current to flow in the reverse direction. What that mean? That means we will use our system or our device and may damage the components. If the voltage bias continues to increase, we will use our device or our system. Why? Because the barrier, the voltage barrier will break down. Now the Schottky diode manufacturing, I take the simplest one. The simplest is to connect a metal wire, here this is a metal wire, against a semiconductor service called point contact. The point contact is here between this right spherical. Some Schottky diodes are still manufactured using this method, but isn't known for its reliability. It's something like disadvantage to this method. The most popular technique is using a vacuum to deposit metal into the semiconductor surface. This method presents an issue of the metal edges breaking down due to the effects of electric fields around the semiconductor plate. The manufacturers will protect this. Very important. The most important line in this slide here, the manufacturers will protect the semiconductor plate with an oxide girdering. Let's talk about this last line. What does mean? Adding this girdering ions will help to what? Will improve the reverse breakdown threshold. Threshold, something like start point, something like that. Not specifically the same meaning, but near. And it prevents the junction from being physically destroyed. Will work to prevent the destroyed situation and improve the reverse breakdown threshold. Why the Schottky diode can switch from conduction to cut off very quickly. This is very important. This is another very important feature, not just the voltage 0.3 or 0.4. This another important characteristic. Let's talk and explain why the energy levels of the electron in the N-type material are chosen smaller than the electrons at the metal side. Therefore, forward voltage is needed for the diode to conduct. When the forward bias is removed from the diode, what will happen? The junction surface is prevented to catch to holding a high level of charge. When the forward bias is removed from the diode, what will happen? The junction surface is preventing to catch another high level of charge. What is the reason of the high transmission speed for Schottky diode? Since p-type material is not used, like I said before, the metal will be instead of the p-type material. Not used in this diode construction, valence band conduction occurs only in N-type material and metal conduction band under forward biasing. That's mean the main reason to the high transmission speed for Schottky diode is the p-type material is not used in the diode construction. Valence band conduction occurs only in N-type. That's mean we don't have valence band at p-type because the metal side will be instead of p-type at Schottky diode. Sorry. Any electric field can be created around the diode, yes, and this electric field will draw to us the limits for the reverse breakdown voltage. Why this type of diode distinguishing feature from the other diode? Like I said before, the most two important features are low forward voltage drop, very fast switching capabilities. And here, this is the last slide. Thank you about your watching. Sorry, thank you about your patience. Let me stop recording. Have a good day.